everyone, welcome back. I wanted to sort of review something that you learned back in Calc 1. When you started off learning about a definite integral, here's the process, right? The idea was that you want to find the area below some graph and above the x-axis, right? So we're looking at the area of this region right here. And the process is that you chop your interval up into some pieces. In each of those subintervals, you just pick a point, and you can just pick the point at random. You go up, you hit the graph. Go up, hit the graph. Up, hit the graph. Each of those points that you chose determines a height of a rectangle, and then if you want an approximation of the region that we're interested in, you add up the areas of those rectangles. That approximates the region. Approximates the area of the region. And then if you want the actual area of the region, what you do then is you let the number of subintervals go to infinity, right? That forces each of those rectangles to get smaller and smaller. It reduces the area, the error, right, of our approximation as those get skinnier and skinnier. And so in the end, the area under the curve above the x-axis is equal to the limit of a certain Riemann sum. Right? So there's the basic idea. What we want to do today is we want to generalize this idea. And so I'm going to go through all the steps. And the way we're going to generalize this is now, instead of having a single curve, what we're going to do is we're going to have two curves. And our goal will be to find the area of the region bounded by those two curves. So let me write the setup here. So let's let let's say f of x and g of x be continuous on the closed interval from a to b, and let's just assume that the graph, the f of x graph is above the g of x graph. So where f of x is greater than or equal to g of x. All right, so in the diagram, then we have f of x here, we've got g of x here. We're looking at the region that lies over the interval from a to b, below the graph of f, and above the graph of g of x. So let's say that. So we'll say, and let capital R be the region below the graph y equals f of x, above the graph y equals g of x, between the vertical lines x equals a and x equals b. So our region capital R is right there. Now, what I want to do is go through the process of finding the area of this region. So here's our region capital R, and our goal, find the area of capital R. And the process I want to go through in detail, and we're actually going to do this process quite a few times in this class. So this is an important thing to pay attention to here. The steps involved in setting up solving this goal, or accomplishing this goal, will be repeated throughout this class a number of times. So step one, what I'd like to do, I want to chop the interval from a to b up into a bunch of pieces. And that's called partitioning. So I'm going to partition the interval from a to b, and it goes like this. A equals x0 less than x1 less than x2 less than ... less than x of n equals b. I want to redraw my diagram a little bit bigger right over here so that you can actually see what's going on a little better. So same picture. I'm just drawing it a little bit bigger. Now, so step one, what we're doing is we're chopping our interval up into a bunch of pieces. Let me finish my sentence. So partition this into subintervals of length. Call it delta x. So I want to chop my interval. In this case, I chose n equal to 4 because I don't want my picture to get too crowded. Right, but so what we have here, a equals x0, then I have x1, x2, x3, and then in this case, b, my last point, is x4. Now, I'm chopping this interval up into equal length subintervals, right? So how long is each one of them? Well, in general, if we chop something of length b minus a into n pieces, then each one of those pieces has length b minus a over n. Right? So delta x, the length of each subinterval, is b minus a over n. Right, so there's step one. And it's always, you'll sort of get used to this as we set up this process. I'll say, okay, what's step one? The correct answer always is going to be partition. Right? The first step, chop the interval up into a bunch of pieces. Step two. Choose. Now what I'm going to do is choose a point x sub I star, so this is a specially chosen point, in the subinterval x sub I minus 1, comma x sub I. So what that means is just pick a point at random, and I'm going to put a dot, right? Just pick a point in each subinterval, right? So in the first subinterval, x0 to x1, I pick a point, and I'm going to call that point x1 star. I guess let me put it down below, at x1 star. In the second subinterval, just pick a point. It doesn't matter. I can pick the midpoint, I can pick the left endpoint, the right endpoint, or any other point in between. And I'm going to call that one x2 star, x3 star, and then the last one, and it does not matter where I choose it, x4 star. So pick a point. And then what I'm going to do, so let's say this, and let R sub I be the rectangle with base delta x and height f of xi star minus g of xi star. So this process of choosing the xi stars is going to allow us to then create our rectangles. So what I want to do is I'm going to go up from x1 star and hit the graph of g and then f. Right? So go straight up, hit the graph and mark that. And then that's going to determine the height of my first rectangle. Then I move over to x2 star. Go up from x2 star, hit each graph, and then draw little horizontals over that second interval. We've determined our second rectangle. And then we're going to do this for each of the xi stars. Go up, hit the graph. That's going to determine the height of a rectangle. Go up, make a rectangle, go up, make a rectangle, so there's R3, and there's R4. In this case, we have 4 rectangles. All right, if we want to approximate the area of the region R, what we can do is add up the areas of these rectangles. So the area of capital R is approximately equal to R1 plus area of R1 plus area of R2 plus dot 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 plus area of R sub n. Now, how do you compute the area of a rectangle? Well, it's just base times height, and so this is going to equal, so let's do it like this. I'm going to use sigma notation here now, so this is sum n equal, not n, I equals 1 to n fxi star minus g of xi star times delta x. This is the height, and that's the base. All right, so here's an approximation of the area, and all it's doing is saying add up the areas of our n rectangles. Once you get those, that gives us an approximation of the total area. And then our final step, if we want the actual area, so step 4, the area of R, well, let's see. What do we want to do? We want to reduce the error by choosing more and more subintervals. Right? They get skinnier and skinnier. And so the area is going to be the limit as n goes to infinity, sum I equals 1 to n f of xi star minus g of xi star times delta x. So what do we call this sum right here? This is called a Riemann sum. So the area is the limit of this Riemann sum, and what we know is if we have continuous functions, then the limit of this Riemann sum can be computed as a definite integral. So it's equal to the integral from a to b of f of x minus g of x dx. Right? So there is the formula for the area between the two curves. And this really shouldn't be too surprising. Let me just draw a picture real quick. Right, if we have a couple of curves, one way to think about finding the area of this region right here is to first find the area of the region below the upper graph, and then subtract away the area below the lower graph. Right? There's a way to think of it, right? That would leave us with this area right here. And that's exactly what this definite integral does. Right? Because you could split this up as two separate integrals. This computes the area below the upper graph, and then we subtract away the area below the lower graph. So I guess my point is this formula should not be surprising. It does exactly what you'd expect geometrically, but I want you to understand how we came up with this Riemann sum, because we're going to do it on a fairly regular basis. We're going to have to develop Riemann sums to compute various quantities as we go through this class. All right, but in the end, to compute the area between two curves, it's a definite integral, top curve minus bottom curve. All right, so let's try some examples now. So first example, and the instructions will be the same. I'm going to draw the picture. So here's our graphs, y equals 8 minus x squared, and y equals x squared. Right? And our goal is to find the area between the graphs of these two functions. If you look at the picture, what we have is a couple of parabolas. So it goes something like that. My picture is a little bit lopsided, but what we're looking for is the area below the upper graph. That's the y equals 8 minus x squared. And above the lower graph, that's the y equals x squared. Now, what we need some limits. All right, so to find the limits of integration, we need to know where these curves intersect. So I need to know that point of intersection and that point of intersection right there. And to do that, so let's find the intersection. And so what we have is 8 minus x squared equals x squared. So x squared equals 4, which means x equals plus or minus 2. So there's a negative 2, and there's a positive 2. And so the area is going to be the integral from minus 2 to positive 2 top function minus bottom function, which we can simplify now. What we get is integral from -2 to +2, 8 minus 2x squared dx. Now, one thing you could do to simplify the computation, remember last time we talked about using symmetry to simplify things. So what we could do, and this is not necessary, but I'm going to do it and talk about it. So what this is equal to is 2 times the integral from 0 to 2, 8 minus 2x squared dx. What this is saying is, I know my picture is a little bit lopsided, but the left-hand side has exactly the same area as the right-hand side. And so if we want, what we can do is find the area of the right-hand side and double it. That's going to give us the total area. And it makes the computation a little bit simpler. So this is 2 times, and now we will have 8x minus 2x cubed over 3, and we go from 0 to 2. The reason for making use of symmetry, that 0 is what makes the computation easier. Right? Just it gets rid of some subtraction that you'd have to deal with. 2 times, this will be so I'm going to plug in my upper limit. That's a 16 minus 16 thirds, right? And then when we plug in 0, we just get 0. So that's going to be 2 times 48 minus 16. I'm just getting a common denominator. 48 minus 16 is 32. And so final answer, we get 64 thirds. Right, so that's the area below the upper graph and above the lower graph. Okay, so some more examples, same instructions. So now what I'd like to do is look at the region bounded by the following graphs, y equals x squared and y equals x cubed. If you draw the picture, here's what we get. The graph of y equals x squared looks like that. It's a parabola. And then the graph of y equals x cubed, it goes something like this. And so what we're looking for is the area in that little sliver right there. All right, so here we have y equals x squared. Here we have y equals x cubed. All right, and we want the area of the region between the two. Okay, so the area is equal to, you need to find the intersection. It's easy to see that the intersection is at 0 and at 1. So the total area will be integral from 0 to 1, top function minus bottom function. And so that's going to equal x cubed over 3 minus x to the 4th over 4. Evaluate from 0 to 1. That's equal to a 1/3 minus 1/4. When you plug in 0, you just get 0. And so this will be a 4/12 minus 3/12, so 1/12. When we went through the derivation, what we had was, I did everything with respect to x. We had a top function and a bottom function. But we can also, let me just draw this real quick. If we have graphs that are in terms of the variable y, so this is an x equals f of y, and this one is a y, x equals g of y, and we have, say, a c, or I guess I should put a c down here, and a d, the same process is going to work. We just have to remember, what does it mean to be top and versus bottom in this setting right here? Up is in the positive direction. All right, so this same derivation will allow us to find the area between curves when our curves are given as functions of the variable x, variable y. That should be a y right there instead of x. So in this next example, here's what I have. X equals 2y squared. And x plus y equals 1. So I can just see mistake in my notes here. That should say x plus y equals 1. All right, so what we have then, now we've got x equals 2y squared. That's a parabola on its side. And then x plus y equals 1. Let's see. That is a line with slope -1, so it looks something like that. So we need to find the intersection. So if I solve here, this is x equals y, 1 minus y, and I'm going to set them equal to each other. So we get a 2y squared equals 1 minus y. 2y squared plus y minus 1 equals 0. Just got everything over on the left-hand side of the equation. And then I need to factor this. And so I'm going to have a 2y and a y. And I think it's going to be a plus 1 here and a minus 1 there. Let's just check. 2y squared plus 2y minus y minus 1. Yeah. Okay, so our points of intersection are y equals 1/2 and -1. So what do we have on the y-axis here? We have a 1/2, and then down here we have a -1. So we're looking for the area of that region there. So the area is going to be the integral from -1 to 1/2 top function, which is the line, minus bottom function, which is the 2y squared. And remember, we're integrating dy. This is an easy integral. I'm more concerned with the setup here. I'm sure everybody knows how to compute this integral right here. And so that's what I want you to understand. It is now the limits on the y-axis that tell us the starting point and the stopping point. Top function is the one farther in the positive direction minus the bottom function. And let's do one more example. So now I want to look at the graph y equals cosine x. Y equals what is it? Sine 2x. And then x equals 0 and x equals pi/2. So if we draw the picture, the cosine on the interval from 0 to pi/2 looks like that, and the sine goes like that. So let's see. So yeah, so here's y equals cosine. Oh, here's y equals sine x, and then we want the region bounded by those two graphs. So what we're looking at are those two portions, those two different sections right there. So if we want the total area, we're going to have to compute two different integrals, right? One for this one and one for this one. And the reason is that the roles of top and bottom get interchanged at this point right here. And I do need to find this intersection point. So for the intersection, we need to solve cosine x equals sine 2x. And the way to solve this, I mean, I guess you can guess and check, but also there's a trig identity that says sine 2x is equal to 2 sine x times cosine x. And so now if we sort of ignore the middle, what we get is cosine x minus 2 sine x cosine x equals 0. Factor a cosine out, we get cosine x times 1 minus 2 sine x equals 0. Cosine of x is equal to 0 at pi/2. That's that intersection point right there. And so this intersection point will be given by solving that one right here. Now what we get is sine x equals 1/2. That occurs at pi/6. So that's telling us the intersection point right there. It happens when x equals pi over 6. So now our area is going to be given by the following formula. Area equals integral from 0 to pi over 6, top function, which is cosine. Oh, and I just realized I made a mistake on my diagram here. That should say sine of 2x, right? It's this function here. So it'll be cosine x minus sine 2x dx plus integral pi over 6 to pi over 2. Now top function is the sine graph, so it'll be a sine 2x minus cosine of x dx. Once again, we've got an easy integral. I'm not going to compute it out. I assume everybody knows how to do it. I'm going to be especially concerned on quizzes and exams with the setup, right? You should be able to compute this on, if the problem says compute it, you do need to compute the integral, but the setup is going to be the important part for many of these geometric type problems. Okay, so that's a good place to stop for now, so we'll see you next time.